Hello, and welcome to the second installment of Chemical Equilibrium, focusing on capital K, otherwise known as the equilibrium constant, not to be confused, as always, for some reason, with lowercase k, that is, the rate constant. So, our equilibrium constant. Even though we know from last time that reactants and products are not the same concentration, obviously there still exists an equilibrium or a relationship between them. And this relationship, I refer to it, or chemistry refers to it, as the law of mass action. A lot of teachers at our school just call it the equilibrium constant, and yes, it is the equilibrium constant. However, in College Board and in the lovely world, some people, most people, I couldn't actually tell you, but I know I call it the law of mass action. Now, law of mass action is pretty straightforward. It's something you probably have seen before, as here in the image to the right. Products over reactants raised to their stoichiometric coefficient. So, unlike rate laws, where you can only use the coefficients as your orders, in equilibrium, you will always use your coefficients as your exponents. So for any given reaction, we always use, or we write the law of mass action, also called the equilibrium constant, as products over reactants raised to their stoichiometric coefficients. And this is the one time you can, quote unquote, forget to put units and not be graded down, because it is a unitless number. Could you put a unit down based on what is you're putting into the math problem? Of course you can, but the unit tells us absolutely nothing. It's garbage. So throw it away. You don't need it. It's garbage. So back up one thing. Sorry about that. Other thing regarding the law of mass action, solids and liquids cannot, will not, won't not be included in the law of mass action. Why? Because they have constant concentration. It never changes. If you have a pool full of water, it's 55.5 molar. If you add a gallon more water to water, it's still 55.5 molar. When you deal with concentration, you're talking basically about ions, things that are dissolved, or you're talking about partial pressures of gases. Solids and liquids are never included, ever. So just leave it at that. So obviously writing equilibrium expression, or the law of mass action, take a reaction, products over reactants, raised to their coefficients. Pretty straightforward, very simple in that sense. That's all it is. Can't really mess this one up unless you don't know states, which then that could mess things up. Now, product favored equilibrium. We have talked about this a little bit in N11. Large values of K. Now, just like everything in chemistry, large, high, low, there's no set number for that. There's no dividing line, so to speak. So, large values of K, we basically just mean values that are larger than 1 to be considered product favored. So, we get a little kind of graph here where once it reaches equilibrium, I have more products than I do reactants. So, product favored keeps it easy. Questions on product favored equilibrium? Okay. So, a large equilibrium constant, again, we're not too worried about the number as long as it's greater than 1. As you can kind of see with this reaction of hydrogen and bromine making HBr as a gas, the little image to the left shows that there's way more HBr molecules than there are diatomic hydrogen or diatomic bromine. And then you have a big number divided by a small number equals a large number. So a lot of the conceptual type questions College Board will throw at you is taking your understanding of the equilibrium constant, how it's set up, and when you start changing things, if you get more numerator or if you get less numerator, more denominator or less denominator as things change, how does that affect kind of what's going on? So kind of keep that one in mind. Reactant favored equilibrium, obviously small values of K, so any value that is less than 1, but, there's a but, greater than 0. Equilibrium constant or law of mass action values can never, underlined, bolded, italicized, 80 font, be less than 0. So, from a graphical standpoint or a pictorial standpoint, we have way more reactants than products. So, here's our way of saying that it's a dividing by a big number. So, my reaction has to be reactant favored and have a equilibrium constant or law of mass action less than 1. So here's an example of nitrogen and oxygen making nitrogen monoxide. You can kind of see from the drawing on the left, only a couple molecules of nitrogen monoxide, but a lot of the reactants. So products over reactants raise their coefficients, going to be a small number. Questions on the equilibrium constant or law of mass action? Okay. All right, so a couple of relationships regarding the equilibrium constant and chemical equations, kind of manipulations, if you will. Obviously, when a reaction is written backwards, the equilibrium constant is inverted. It's just the reciprocal. So you have to know how it's given originally in the problem, and then if they reverse it later on, then you know it's the reciprocal of your actual number. So easy one there. So for example, we have this reaction of AB goes to C plus D, and we get this lovely thing. But then let's reverse it. Of C and D goes to AB. It's, again, just reciprocal. Pretty straightforward. College Board will probably have you solve for the equilibrium constant in the forward direction. And then part F in the problem, they will give you the same reaction written in reverse. They won't tell you that, of course. And then ask you for the equilibrium constant of this reaction. You need to come to the realization that it's written in reverse of the earlier part of the problem. So just take 1 over your answer and call it a day. Don't need to rewrite the equilibrium constant. It's just 1 over the earlier answer and move on. So we know K backwards or K reverse is just 1 over K forward. Same idea. All right, so when the coefficients of an equation are multiplied by a factor, the equilibrium constant is then raised to that factor. So here's again our A plus B goes to C. We have our reaction. Apparently D didn't make it to this slide, so I apologize for D. Didn't really want to include them this time, but, you know, life happens. And then we're going to multiply through the reaction by 2. This reason why. Why am I multiplying by 2? Well, for the slide, it's just for the sake of multiplying by 2. But when you have multiple reactions and you can manipulate them similarly to Hess's law, instead of multiplying delta H by your factor, here with equilibrium, if you multiply by some factor, you have to raise it to the power of that factor. So, similar to Hess's law in the manipulation aspect, reversing it, multiplying it, dividing it, but with equilibrium, you have to then raise it to that power, because as you can see from here in the lovely purple, that's the effect it's going to have. Questions on this one? Okay. Oh, anyway, so K nu is K raised to the N, whatever you multiplied by of the original. Got ahead of myself on that one. I apologize. All right, so relationship with K and chemical equations, as I've kind of alluded to. When you add equations to get a new equation, the equilibrium constant of the new equation is the product of those equilibrium constants of the old ones. So we have these two reactions of A goes to B and B goes to C. So K1, B over A, easy enough, we're good on that one. Equilibrium constant of the second one, C over B. Again, you've done this before, nothing new. But I want the overall reaction of A goes to C, is what I'm looking for. So I know that it's C over A. In order to get that, I have to multiply the law of mass action for reaction 1 and reaction 2 in order to get B to cancel out. So because I multiplied the law of mass actions, I then have to multiply the actual numbers themselves. So K new is just K1 times K2. Keep in mind, if you had to do some manipulation of reversing or multiplying or dividing by some factor, you would have to do that before you multiply individual K's together. Not after the fact. Whatever you do in manipulation to K1 or K2, apply that manipulation to get a new number before you do the overall multiplication. Questions on this idea? All right. So, equilibrium involving gases, nothing's really changed. It's still the law of mass action. Nothing's changed except we're dealing with gases instead of concentrations, as in dissolved in water. So, partial pressures, we can express this as a ratio of partial pressure of gases. So, oh look, it's the exact same. Watch out. Now, K sub C, concentration. K sub P, as in Paul or pressure, is in terms of pressures. Now, College Board invariably will ask you to write this expression based on the reaction that is given. If it's molarities, you write the one on the left. If it is pressures, they're going to expect you to write the one that's on the right, and maybe using parentheses instead of brackets. Brackets represent concentration, but when you deal with pressures, capital P sub whatever that thing is, raised to the coefficient. So you're still doing products over reactants raised to the coefficient. One uses brackets, one uses parentheses, or written like this. I haven't really seen much in the grading that if you were to accidentally do concentration or brackets, even though the reaction is written as partial pressures, that they deduct a point or they don't give you the point, I haven't seen that, but it's just in your best interest to stay consistent with concentration brackets, pressure, use parentheses. Questions on the difference, if any? All right. All right, so Kc and Kp have a relationship. This relationship is no longer part of the course. So they used to have this equation on the equation sheet. It has been since removed. So mathematically, you're not going to do anything. But, in calculating Kp, partial pressures are always in atmospheres. That's one to keep in mind, that when you do anything with a pressure type thing, if they don't tell you the unit, atmospheres. Go with atmospheres. Our values of Kp and Kc, they're not necessarily the same. Obviously comes down there, because of different units. One being molarity, one being atmospheres. They're not really relatable in that sense. That's not a negative sign. But we do know that Kp and Kc are equal when the change in coefficients equals 0. And we get this lovely equation. Looks like this. Again, you don't need to have this really known mathematically. And again, it's you look at your reaction. If, let's say, they're all 1s, then the difference between reactants and products is 2 minus 2. It's still 0. So there's no effect in that sense. But again, don't need to worry about it for this class. And as you can see, just to make sure we're on the same page, difference in the number of moles of reactants and moles of products, which does come from your coefficients. Here's the derivation of it. You can come back and check out it later, because I'm not going to spend time, because we don't need to. A lot of stuff going on here. See? A lot of fun stuff. And notice N, like everything else, is products minus reactants. That hasn't changed. Alright, heterogeneous equilibria. Kind of alluded to this earlier, that only aqueous and partial pressure can be in the law of mass action. So we know concentrations of solids and liquids, they do not change. Their amounts change. Please note, there's a difference between the amount that you have of something and the concentration of it. Because solids and liquids do not change concentration, they're not included. As we just said, yay. So our equilibrium expression for this one, hydrogen and bicarbonate and CO2. There's my reaction in the wrong spot, out of order. But notice water is not in it. Water is a liquid, so it's just not included. So another kind of idea of looking at what's going on. We have way more carbon in the jar on the right than we do on the left. But because I have more carbon, it's a solid. The amount of CO2 and the amount of carbon monoxide at equilibrium under the same conditions doesn't change. Doesn't affect how much solid you have. Questions on that idea? Okay. Alright, looks like we're done. One quick thing. Gotta remember that we saw in thermodynamics the equilibrium constant, the law of mass action, depends, in bold, underline, italicized, highlighted, font size 812. The equilibrium constant depends on temperature. If temperature stays constant, the numerical value will never change. There are infinite positions of equilibrium that will give you the same numerical value. And we're good. Any questions? Bye-bye.